Hello, statistics student. This video is for chapter 8.2, confidence interval for mean with one sample when sigma is not known. So this is very similar to 8.1. Our goal is to find confidence interval for population mean. But the problem is we don't have sigma, okay, which is quite common. So we say in real life, actually, if you don't even know your population mean, why would you know your population standard deviation? So most of the time we do not have population standard deviation. This is in very rare situation you might know standard deviation sigma. Okay, so although CLT, the central limit theorem, guarantee that sample mean are normally distributed, so we can say, okay, so the largest error is how many tick mark of sigma over square root n, so I know how the large E is. But if you don't have sigma, you can't. So can I just use the sample standard deviation S over square root n to replace it? When n is really, really big, maybe okay. But if your sample size is really small, even less than 20, that may be an issue, especially if S is like a big number. So S may differ from sigma a lot, just for the size of it. So you cannot just use this to represent sigma. So we would want to actually replace, instead of using Z, we would use this. Each tick mark would be S over square root n. That's what we do. But instead of counting them as Z, we count them as T. Okay, it is called a T distribution. And then what the T graph is actually still normal, kind of like Z. In Z, we would say 0, 1, 2, 3, like that. They still have that. They still have 0, 1, 2, 3. Remember, this T is the number of tick mark of S over square root n for X bar. So this is for X bar only. Okay, -1, -2, like that. But what happened is, so if this is, if this is a T, this is a Z. Z is sharper and the tails are lower. So T distribution usually had a higher tail area. Also, T distribution, so we'll talk about those later, is depends on sample size. So there's something called degree of freedom is n-1. So if you have different sample size, your T distribution looks different. The tail areas look different. So this is how it look like. If the middle is sea level, the 2n would be alpha together. So this will be alpha over 2. You would use a inverse T calculator to find T alpha over 2. Okay, so online stat book had a inverse T calculator like this, inverse T calculator that give you inverse T distribution that tells you enter degree of freedom and you tell them which the middle sea level, and then they will give you the T critical value for the confidence interval. Okay, so you use inverse calculator. It's not as flexible as the inverse normal where you can have any sea level. You can only have these three. Other calculator can have different numbers, but I think this one is good enough. Okay, so if we have the T critical value, we would have the formula, right? So we'll say, okay, to find the error bound, I would use the tick mark, T alpha over 2 with the alpha over 2 at the tail end, multiplied by each tick mark size, which is S over square root n. So the interval would be X bar minus E and X bar plus E, just like before. We call this the lower limit, and this number is called the upper limit, so that your population mean will be between these two numbers. And remember, in this case, when you use T, is because you have no sigma. You cannot use Z because you cannot count sigma over square root n tick mark. So the key word is you use T distribution, student T distribution when sigma is not known or given. So You can also do online calculator to find the confidence interval. So, but before we go over that, let's look at how we can calculate by hand once. Okay, so we have a sample size of 40, which guarantee that x bar is normal. And then the sample mean is 76. Sample standard deviation is 6.5, but no sigma, right? So we must use t. So what's the critical value for 90% confidence interval? So go to inverse t, this things, and we say it's 90%, right? And my degree of freedom was what? Oh, because n is 40, so degree of freedom is 40 minus 1, right down is 39. So t would equal to, let's change this to 39 and I do calculate, it's 90%, 1.685. So I can calculate the error bound using the formula. Error bound is t, this number t over 2, or I can just say t, and then s over square root n, because this is the tick mark. 1.685 times s is 6.5, square root of 40. So put in the calculator, that would be 1.685 times 6.5 divided by square root of 40 is 1.73. If I want to round to 2 decimal places, find the confidence interval. So we would say is x bar plus and minus 1.673, right? So that means is 76 plus and minus 1.73 plus and minus e actually. So that would be lower number, lower limits at 74.27. Upper limit, upper bound is 77.73. And if you want to, you can write the interval notation 74.27, comma 77.73 also, okay, by the calculator, hand calculator. So this is calculate everything by hand. It's not too complicated. The most difficult one is to find the critical number, which is the number of tick mark. But the online statistics calculator can do it for you, or they have programs that help you do this. You need to provide C level, X bar, C level, X bar, S and N, or you will provide data. And if your data is in comma list, you would use the LibreText calculator. So show you how it look like is that this is just still the same confidence interval, mean one sample. You would click either summary statistics if you have these number, or you say use data. But your data must be, in the vertical column. So use summary statistic, you have to provide this, but you do not put population standard deviation, because population standard deviation is for Z. So if you put this, then they would not use T. Okay. Let's do look more details on what is a T distribution. So T distribution is, what is it? It is the number of times S over square root n. X bar is from mu. So basically it's a statistics of X bar minus mu over each tick mark being S over square root n, if X bar has a normal distribution. So T distribution is different from different sample size. So it has a degree of freedom called n minus 1. Each T distribution is more or less symmetrical as standard normal, but with more variability. That means the standard deviation is not 1. The standard deviation is a little bit higher. So there is a interactive. So that I think there is a program that compare the student T's distribution to the normal's Z distribution. So here, if you have a sample size 6, the red line is T distribution. You see how it is higher at the two end. The black gray line is Z distribution. Okay, so it has less error at the end, less variable at the end. But if you move your cursor to like close to 20 over, this, then you pretty much have the same like area as Z. So they become more or less the same when sample size is large. Okay, so some people would say if you have a large sample size, you can just replace, you can just use S over square root n, as if you are doing, the with sigma. So, but when it is small sample size, you can see that there's a big difference. The C distribution is sharper, but lower tail. Okay, and also because the formula is to calculate the margin of error is t times s over square root n. If sample size increase, you divide by more number. If sample size increase, this will be decrease, right? If you decrease the sample size, you divide smaller number. This will increase the error will increase. To interpret the confidence intervals of mean is the same as before. You just say that you have certain confidence that the true population mean for whatever that you're measuring is between, whatever population is between the upper and the lower limit. And also all the confidence interval you measured with that particular sample size, only that sea level percentage contain the true one. Okay. To make conclusion is the same before. You have to look at the whole interval. So if the whole interval is greater than a number, then you say mu is greater than a number. If the whole interval is less than a number, you say it is. And any value in the confidence interval can be mu. So remember, the confidence interval tells you that your mu fall into one of the value. So one warning is never make conclusion about population mean solely based on the value of x bar. Okay, let's go to the next page, which is do an example. So this example is patient with insomnia are treated with sopiclone. After treatment, the 16 subject had a meal wake time of 98.9. How do I make sure the X bar is normal? So we have to be careful. So it is X bar is normal because the wake times are normally distributed. So I don't need a big sample size because the original distribution is normal. And it turns out that this is the mean wake time. That means this is from a sample. So this 16 subjects means this the sample size is 16. And this is the mean wake time of those people. So this must be X bar. Sample standard deviation S, right? S equal to this. So we write this down and we want to do 90. Is it? Why do I say 99? Oh, it must be a typo. So I should say 99. Right? Sea level is 99 because later on, I think I didn't do it here. So it's 99, N is 16, X bar is 98.9, S is 42.3. So maybe I'll write it down here. 0.99, N equal to 16, X bar equal to 98.9, S equal to 42.3. So we want to find the critical T at a 99. So go to, this is the inverse normal, no? So what is the degree of freedom? Our sample size is 16, so our degree of freedom, we want to do degree of freedom first, right? Degree of freedom is 16 minus 1 is 15. So we should say 15 and then it's 99. 2.947. So, so T equal to 2.947. Okay, so we would find, because, so we use T distribution, of course. We do not use T, so T is 2.947. Degree of freedom is equal to 15. So construct 99% confidence interval. So to construct it, what you can do is, this may be wrong, okay? Because I think at one point I do 98, but it should be 99. So let's construct it with stat this, okay? Stat this. and analysis confidence interval. Whoops, as the analysis confidence interval